So in this example, we have a disk with a radius of 50 centimeters rotating at 600 revolutions per minute. And it comes to a stop after making 50 whole revolutions. The question here is, what is the acceleration? Well, we have a final omega value of 0 RPM. We have an initial of 600, and we have a theta of 50 revolutions. So, we need to do some conversions, but we can say that the equation we need is 2 alpha theta, which is equal to the change in omega squared. And you can see the linear analog of 2AS here. First we have to convert. We have 600 revs per minute, and we want to convert that into radians per second. So we'll take our 600 revolutions a minute, multiply by 2 pi, and divide by 60, and that'll give us 62.8 radians per second. 50 revolutions is 314 radians. So now alpha, we know that omega f is 0, is equal to the initial omega squared divided by 2 theta. Theta was 314 radians. Substitute in, and we'll end up with an alpha value of negative 6.29 radians per second per second. So this is an alpha that is acting opposite to the direction of motion. Continuing our discussion about acceleration, there's a very special case involving centripetal acceleration. And by centripetal acceleration, we mean that there is going to be an acceleration as you move something in a circle that acts from the edge of that circle towards the center of the circle. For instance, if you swing a ball on the end of a string, there will be a tension in that cord. That means there is an acceleration acting from the ball on the end of the string towards your hand at the center. This is centripetal acceleration. Now, the special case here is that if we rotate an object at a constant speed, you will still experience a centripetal acceleration. Now, that means if speed is constant, how do we end up with an acceleration? And no, I'm not making a mistake here, as it's often assumed. Centripetal acceleration depends on the change of a velocity vector. That means you can keep the magnitude of the overall velocity vector the same, but you can constantly change the direction. And that's what's going to happen if you swing something in a circle. You will have a linear velocity at every single point in that circle. And as you swing something in a circle, the linear velocity will be changing infinitesimally at every point in the circle. Not omega, but v, the straight line velocity. Because the velocity vector is constantly changing direction, you will end up with an acceleration acting towards the center of the circle, a centripetal acceleration. So what we're saying is, take this ball and rotate it around in this circle. As the ball moves from this point to this point, v1 and v2 will be the same magnitude, the same length. But look at the direction of the vector. The vector is constantly changing in direction. This gives an acceleration this way, along the string or whatever tether is here, from the outer edge of the circle towards the inside. Excuse me. We can resolve that system by triangles, of course, and say here we'll have a change in velocity over v. That's going to be delta r over r. If we solve a v, we can say delta v is v over r times the change in the radius here. Using acceleration, delta v over delta t, we can substitute in, and we can say delta v over delta t is acceleration. Put it into here, and what we'll end up with is this useful relationship. that centripetal acceleration, the acceleration towards the center of the circle, AC I tend to call it, so we're not mixed up with a tangential acceleration or a translational acceleration, is equal to v squared over r. Now the important thing is here that this centripetal acceleration and the velocity always act at 90 degrees. And the velocity is always tangential to the circle. So the centripetal acceleration, AC, always acts towards the center of the circle in this fashion. So there's our directional vector v pointing at a 90 degrees constantly to where the circle is. It's a tangent from the circle at all points. As the system rotates around, v constantly changes direction, giving you this centripetal acceleration a towards the center of the circle. So please be aware, you now have another acceleration to think about. You have an angular acceleration, a linear acceleration, and now you have a centripetal acceleration as well. And if we think about that, we can say v is equal to omega r. Of course, then omega in terms of v is v over r. But AC, centripetal acceleration, can be v squared over r or r omega squared. I often simply convert here. If I have r anyway, I like to put things in terms of v and r to make sure I'm getting it right. But either of these two relations is perfectly valid. And that's really where that comes from. You can follow this derivation through and say that centripetal acceleration becomes v squared over r or r omega squared. Now, when we're dealing with forces, if we have a centripetal acceleration, we will of course have a corresponding centripetal force. This is not some new relationship here. All that centripetal force is the force with some new expression for centripetal acceleration. So it's the same old F equals ma that you've always seen, only no a is equal to ac. So in F equals mac, we can say here that F is equal to mv squared over r or mr omega squared in the case of our centripetal force. So centripetal force here does not have its own relationship. It's just F equals ma, where a is v squared over r. So let's take a look at a question. Here we've got a ball of mass 0.5 kilograms attached to the end of a cord of length 1.5 meters and then whirled in a horizontal circle. What this means by horizontal circle is above your head in a flat circle. We're not talking about something that's a vertical circle. If it was vertical, then gravity would be assisting the ball on its way down. This is a horizontal circle, like holding a flat plate in front of you. Now the question is, if the cord can withstand a maximum tension of 50 newtons, what's the maximum tangential speed, that's v, of the ball before the cord breaks? So there's the situation. We've been talking about this kind of thing all the way through, putting a ball on the end of a string. Your hand would be here, and you'd be whirling this over your head in a circle with some velocity v at all points. So here, the centripetal force is the tension in this string here at r. So Fc is equal to T. That means T is mv squared over r. If we want to find out what v is, we can simply rearrange and end up with v being root tr over m. So Fc is mv squared over r, or T is Fc here. That means v is essentially tr over m. Substitute in our values of 50, 1.5, and 0.5 for the radius, and that will give us root 150, which will give us about 12.2 meters per second before the string snaps, the ball flies off, smashes a vase, and you spend the afternoon trying to put it together before your mother realizes you destroyed it. A similar thing also occurs in cases where there is no tether. It's easier to visualize a tethered case where there's actually a cable attached to an object that's whirling around. But if you think about something like a vehicle taking a corner, now as this vehicle goes into the corner, it's going to have velocity vectors or force vectors here from the tires. That means as the wheel rotates, a force vector from the tire acts backwards, propelling the car forwards. In this case, here are the vectors. So this is essentially the tire vector, and this is the force vector of the vehicle. As the vehicle goes into a corner, you've still got a force vector forwards, and of course a velocity forwards. Now, essentially, what's going to happen here is the tire's force vector is going to try and hold this vehicle on the road. Now, the idea of something like a tire is it's engineered to keep you on the road. So as you're going around this corner, this vehicle does not screech off and smash into the scenery. So this act here, this force here, essentially acts in a very similar way to having a tether. So think Batman, the original Michael Keaton Batman movie. He fires this grappling hook out around a light pole and swings himself around a corner, if anyone's seen this. That would kind of work if the light pole actually didn't rip out of the floor. So essentially, this force vector in this direction is a force vector acting towards the center of the circle, acting towards the center of the radius. And this force vector will balance this force vector outwards as the vehicle goes into a turn. This is why tires, for multiple purposes, such as the tires you have on your vehicle, will have sort of zigzag patterns and straight line patterns. Not only do they want to grip and give you a forward velocity vector, they also have to take velocity vectors from the side while you're taking a corner. So you can see going in, the velocity vector from the tires is straight backwards, the vehicle forwards. In the side and in the curve, the velocity vector on the tires will be from the side. And then as you come out of the curve, the velocity vectors will be in a straight line again. So the question becomes, if we have a 1500 kilogram car and it's moving around a curve of radius 35 meters, so this is the curve and this is the radius of that curve on a flat road. So don't worry about it bumping up and down. We've got a mu s for the tire on the road. It's mu s because it's the mu between the tire and the road that stops this vehicle slipping and moving sideways. Not this way, but this way. What's the maximum speed that the car can negotiate the turn? So very similar to the ball problem we saw, but now there's no tether. So we want to find out what force balances the centripetal force. What do we know? Mu is 0.5, m is 1500, r is 35, so quite a lot. I've got mu quoted twice there. And what's the velocity? That's what we want to know. So F is equal to mv squared over r. But it isn't quite that simple. Not only is F mv squared over r, it's also mu n was equal to mu mg. So we're saying we have to balance the centripetal force with the frictional force. So if you thought you weren't going to see frictional force again, think again. So mu mg here is going to be 0.5 times 1500 kilograms times 9.8. That gives us 7,350 newtons. Now, if we look at our equation, mv squared is equal to mu n, which equals to mu mg, mass is on both sides of this equation and cancels out. So, v squared over r is just mu times g. So we don't even need the mass at all for this particular calculation. That means if we want to find out v, we can rearrange and say v squared is mu rg. If we root that out, 0.5 by 35 by 9.8, we get root 171.5. So the velocity becomes 13.1 meters per second. So that's the end of us talking about rotational kinematics. Next time, we're going to get into talking about rotational kinetic energy.